This is lecture 2 of differential equations, models, and epidemiology. This lecture is about the SIR model. The SIR model is the original model developed by our friends McKendrick and Kermack in the 1920s, and it is still probably the model that is most often referred to in epidemiology. Here's the situation described by the SIR model. It's similar to the situation described by the SIS model from the first lecture, but with a little difference. So this time we consider an infectious disease from which people recover and then have complete immunity. We'll assume that the immunity is permanent, lasts forever. We consider a population of people who interact with each other. And this time we divide the population into 3 compartments: susceptible, infective, and recovered. This time, after you're infective and you recover from the disease, you go into this new compartment. We'll use S of t to denote the population fraction of susceptibles at time t, I of t to denote the population fraction of infectives, and R of t to denote the population fraction of recovered. S plus I plus R is going to be 1 because all the fractions have to add up to 1. And each of these quantities is between 0 and 1 because they're population fractions. So the differential equations that we have this time are very similar to the differential equations for the SIS model. S dot is minus beta SI, much as it was before. Previously, we had a plus gamma I term because infectives return to the susceptible class, but this time they're not going to return to the susceptible class. For I dot, we have exactly the same equation we had in the SIS model, beta SI minus gamma I. And we have a new equation for the recovereds. R dot is gamma I because the infectives, when they recover, go into this new compartment. The constants beta and gamma are the same as they were before. They have exactly the same meaning. And we still have this important quantity that's calculated in epidemiology, R naught, beta over gamma, which represents, just as before, the number of people that an infective passes the disease on to at the start of an epidemic when everyone is assumed to be susceptible. So the SIR model is a system of 3 equations. Let's notice that if we calculate S dot plus I dot plus R dot, if we add up all the terms here, everything cancels. So S dot plus I dot plus R dot is 0. That means that S plus I plus R is a constant. And in fact, it's 1. It starts off being 1 and it stays 1, as it should be if the model is correct, because the population fractions have to always add up to 1. So we can always recover R from S and I. R is 1 minus S minus I, since they add up to 1. So we will only use differential equations for S and I. We don't need a differential equation to recover R. So S dot and I dot are the first 2 of these differential equations. This time we don't even need to make any substitutions. So this is a differential equation in the plane. The coordinates are S and I, but we don't care about the entire plane. So here's the S-axis and the I-axis. So what do we want for S and I? We want S and I to be greater than or equal to 0, so we want to be up here, but we don't want S plus I to add up to any more than 1. If S plus I added up to more than 1, then R would be negative, and that's not allowed. So here's the line, S plus I equals 1. We want to be down below this line, so we want the points, our points SI to be in this triangle, which we call T. T is what's called phase space. It's the portion of the plane that's important for our problem. whenever we look at this triangle, let's just bear in mind in interpreting things, we'll have a point SI in here, but there's always an R value associated with it. R is 1 minus S minus I. The number of, we see a point here gives us the number of susceptibles and number of infectives. There's a number of recovered associated with that. Perhaps I'll point out here that the SIR model can also be used for diseases that are sometimes fatal. We're ignoring that for the moment for simplicity, but we'll discuss that at the end of the lecture. Nothing changes with the model. We're interested in solutions to this differential equation. How can we understand them? So the first thing I want to say is that a differential equation, any differential equation, x dot equals f of x, defines a field of vectors, a vector field. The vector at any point x is this vector f of x, and it's drawn with its tail at x. We are going to try to roughly draw the vector field defined by the SIR model. So to draw a vector field in 2 dimensions, what you would do is first draw the null clines. These are the curves where x1 dot is 0 and where x2 dot is 0, if x is x1, x2. And wherever the null clines meet, where x1 dot and x2 dot are 0, that's where we have equilibrium. For the SIR system, we only want to look at the vector field defined by the equations on the phase space, which is the triangle we just talked about. Here's our differential equation. What we want to do is calculate the null clines. There's some null clines for s dot equals 0. And to see where this equation is 0, that's very simple. It's 0 where s is 0 or where I is 0. In other words, the s dot equals 0 null clines are simply the axes. What about the I dot equals 0 null clines? Okay, so this is easier to figure out if you take the equation for I dot and factor out the I. So then I dot is 0 where one of the factors is 0. I dot is 0 when s equals gamma over beta. That's going to be a vertical line, or when I is 0. So first of all, let's talk about the equilibria. On the line I equals 0, which is the s-axis, both s dot and I dot is 0. So the entire s-axis consists of equilibria. Now let's discuss the general direction of the vectors. We're just going to try and figure out whether the vectors point up and to the left, down and to the right, up and to the right, and so on. In other words, we're just going to try and figure out where s dot is negative and positive, where I dot is negative and positive. So let's look at s dot first. Let's look at this equation up here. We want to know where s dot's negative and positive, but we only care about the region where s is positive and I is positive. And in that entire region, s dot is negative. So s dot is negative in the entire region that we're concerned with. What about I dot? This variable I is positive in the region we're concerned with, but this term here changes sign. When s equals gamma over beta is 0, when s is less than gamma over beta, this term here will be negative, and so I dot will be negative. When s is bigger than gamma over beta, this term will be positive, and so I dot will be positive. So what does this tell us? Well, there's 2 cases, depending on whether R naught is less than 1 or bigger than 1. You may remember these cases came up with the SIS model. R naught's beta over gamma. Suppose it's less than 1. Then that means this number of gamma over beta is going to be bigger than 1. So in this case, I dot is negative everywhere in the region we're interested in. We're only interested in s going up to 1. Gamma over beta is bigger than 1. Everywhere in that region, I dot will be negative. So in this case, where R naught's less than 1, in the entire triangle that we're interested in, or at least the positive part of it here, Both S dot and I dot are negative, so the vectors point down and to the left. That's all we're trying to indicate here. Over here on the line S equals 0, you may remember was a null line. On S equals 0, S dot is negative. That means that the vectors only have a vertical component, an I dot component, and I dot's negative everywhere. The vectors point straight down there. Okay, now let's look at the case where R naught is bigger than 1, beta over gamma is bigger than 1. So that means that gamma over beta is less than 1. And this null line here, where I dot is 0, this vertical line lies in the middle of our triangle because gamma over beta is less than 1. Right. Now, we're still going to have S dot negative everywhere, but this time I dot will be negative to the left of that line, and I dot will be positive to the right of that line. So S dot's always negative. We're always moving to the left. To the right of that line, vectors point up, I dot's positive. To the left of that line, vectors point down, I dot's negative. Right on this line, I dot is 0. So the vector's horizontal, and we know that S dot is negative. It points to the left. Over here on this y-axis, we know the vectors point down. Okay, so we get the general direction of the vector field just by thinking of the signs of S dot and I dot. Now, what are the orbits of the SIR system? An orbit of a differential equation is the curve and phase space that is traced out by a solution. So if we had a solution of this differential equation, as time goes on, it would trace out a curve in SI space, and that curve is called an orbit. So we're going to try and figure out all we can about the orbits of the SIR system. So orbits are tangent to these vectors. The vectors are actually the velocity vectors of solutions, and the orbits are the curves traced out by solutions. In fact, one way to think about a differential equation is it's kind of like a connect the dots puzzle that children do. In a connect the dots puzzle, you're told to go from dot number 1 to dot number 2. A differential equation is like an infinitesimal connect the dots puzzle. You're just told the direction you're supposed to move. Of course, as soon as you go a tiny way, then the vector is different, and you've got to go in that direction. What can you learn about the orbits from just looking at the vector field? So first of all, whenever I equals 0, like we said before, there's going to be an equilibrium. You can have a line of equilibrium here. It's good to think about what that means, whether it makes sense or not. In this case, what we're saying is we have an equilibrium whenever the population fraction of infectives is 0. If there's no infectives, then no susceptibles get the disease. Nobody moves into the recovered compartment. Everything just stays the way it is. That's why there's an equilibrium. And there can be equilibria with any number of susceptibles. The remaining population fraction would consist of recovereds. Okay, let's look at this vertical axis, the y-axis. So you may remember we said that the vector field was vertical and points down. So an orbit that starts on the y-axis will just move straight down. The solution will just move straight down and tend toward this equilibrium. What are we saying? We're saying that if there are some infectives, but there are no susceptibles, then the infectives can't pass the disease on to anyone. They're not going to cause any change in the number of susceptibles, which is 0. There aren't any susceptibles. The infectives are all just going to gradually get well, and their number will decline to 0. Let's look at the interior orbits here when R naught is less than 1. When R naught is less than 1, what happens is that solutions go down and to the left, and end up at some equilibrium. They go to the left because the infectives are passing the disease on to susceptibles, so the number of susceptibles is decreasing. But because each infective passes the disease on to so few people, the number of infectives is also gradually declining, and eventually the disease dies in. That kind of makes sense. What about over here when R naught's greater than 1? That's when diseases can get started. So if we look over where the number of susceptibles is more than gamma over beta, we see that the arrows point up and to the left. So the number of susceptibles is decreasing. You know, susceptibles are getting the disease and leaving the susceptible category, but the number of infectives is increasing. The epidemic is spreading. Eventually, we get to this point where the number of susceptibles has declined to gamma over beta. And at that point, the number of infectives stops decreasing. There's just too few susceptibles to pass the disease on to. The number of infectives starts decreasing. The number of susceptibles is still decreasing because they're still getting the disease, but now the disease eventually dies out. So we can learn all this about the SIR system just by looking at this rough sketch of the vector field. Let's ask one more question about our vector field in the triangle. If a solution starts in the triangle, does it stay in the triangle? Well, it's certainly better if a solution left the triangle, like through here, then S plus I would become greater than 1, R would become negative, and that would be very bad. We don't want that to happen. This is just a check that we have a good model. All right, solutions are not going to lead through the I-axis. They're not going to lead through these equilibria. But what about through this line? Could solutions lead through this line? When R naught is less than 1, solutions point down and to the left, so we immediately enter the interior of the triangle. Solutions don't leave. What about when R naught is bigger than 1? Up here, solutions point down and to the left, so that's not a problem. But over here, they point up and to the left. Is it possible that they point up and to the left like that and take you out of the triangle? So let's look into that. The top boundary of the triangle is S plus I equals 1. Let's look at how the function S plus I changes along a solution. This is often useful to look at how a function changes along a solution of a differential equation. Because you see, if S plus I decreases, that means you're moving into the triangle. If S plus I were to increase, you'd be moving out. So let's look at V dot. It's S dot plus I dot. This is how V is changing in time along a solution. What is S dot? Use the differential equation. It's minus beta SI. What's I dot? Use the differential equation. It's beta SI minus gamma I. These two terms cancel. And so we get that V dot is minus gamma I, which is negative whenever I is positive. So it's not negative here when I is 0. Those are equilibrium. Whenever I is positive, S dot plus I dot is negative, which means that we're moving into the triangle, not out of it. That's good news. Let's go back to the orbits. So those are curves in SI space. For some planar systems, you can actually find an equation for the orbits, not always, but sometimes. And that is the case for the SIR system. So here's how you can try and do it for any planar system. Write the system not with that S dot notation, but with ds dt and di dt. Don't use the dot notation. So this is something you've encountered in calculus. The solutions of this differential equation are parameterized curves. You may remember if you wanted to look at the curve that a parameterized curve traces out for getting time, you can just divide di dt by ds dt. And what you get is di ds. And then you divide the right-hand side, so also divide this by this. Beta si divided by minus beta si gives -1. Minus gamma I divided by minus beta si gives plus gamma over beta s. All right. So you divide the two differential equations, and what you get is di ds. You get a differential equation in the plane in SI space. If you find the solutions of this differential equation, there'll be curves in SI space. They'll be the orbits. So this differential equation is easy to solve. You just take the antiderivative with respect to s. So I is just minus s, that's the antiderivative, plus gamma over beta log s, plus some arbitrary constant. This is a collection of curves in the plane. They should be the orbits. Okay, so here we actually plotted a bunch of these curves using a computer. They're doing what we thought, heading down and to the left when R naught is less than 1. Here we plotted things when R naught's a third, going up and then down when R naught's bigger than 1. Here R naught is 3. Well, I guess I lied a little. Because one of these curves is actually, it extends down into I negative like that. So one of these curves is not really an orbit. Actually, what you find when you find the solutions of that differential equation on the last slide is you find what's called invariant curves. They're curves such that if you start on them, you stay on them for the differential equation. And these invariant curves are unions of orbits. So here we see one of these curves, and even when we look at it in the triangle, it's not a single orbit. What we actually see there is 3 orbits. This is one orbit, and each equilibrium is an entire orbit by itself. That's because solutions that don't start at equilibria never reach equilibria. And solutions that start at equilibria stay there for all time. We actually discussed this for the SIS model. Let's just go through it in a little more detail. Why is it that solutions cannot reach equilibria? So suppose the differential equation x dot equals f of x in any number of dimensions has an equilibrium x1. So that means that f of x1 is 0. And let's suppose we have a solution x of t that's heading toward an equilibrium and reaches x1 at a time t1. So that x of t1 is that equilibrium x1. That means that x of t is the solution of the initial value problem, x dot equals f of x of t1 is x1. But the solution of that initial value problem, since x1 is an equilibrium, is just x of t is identically equal to x1. You stay there always. So x of t was always at x1. Solutions can't arrive from somewhere else at x1. If they're at x1, they were always at x1 in the past and in the future. On the other hand, like we said for the SIS model, solutions can approach equilibria. They just get closer and closer to it as t goes to infinity. That's if they approach it in forward time. If they approach an equilibrium in backwards time, they get closer and closer to it as t goes to minus infinity. This is correct mathematical theory. In practice, as a practical matter, we say that solutions arrive at equilibria. They get so close to it that you can't tell the difference. Let's look a little more closely at this phase portrait when R naught is greater than 1. So a lot of the solutions they appear to start at one equilibrium, which I call S minus, because that's what's being approached at minus infinity. They start at one equilibrium S minus, where S minus is greater than this number gram over beta. The epidemic takes off, the number of infectives increases. Eventually you cross S equal gamma over beta, the number of infectives starts to decrease. And as time goes to infinity, you approach another equilibrium, which we call S plus, because it's approached as t goes to plus infinity. So how many people got sick during that epidemic? So we started off with 0 infectives, S minus susceptibles. The remaining part of the population, R minus, 1 minus S minus, recovered. They have immunity. This disease must have been around in the past. Some people got it and they recovered. They have permanent immunity. So the next time the disease comes around, the entire population is not susceptible. Only a part of it is. So the disease takes off and then dies out right here. At the beginning, the number of susceptibles was S minus. At the end, the number of susceptibles is this smaller number, S plus. You can see the number of people that got the disease. It's S minus minus S plus. The amount that the number of susceptibles decreased is the number of people who got the disease in the course of the epidemic. How would you calculate that? Given S minus, for example, if you knew that, if you knew the situation when the epidemic started, how would you calculate S plus? Here are the invariant curves we found. If one of these curves passes through S minus 0, then that point is on the curve, so just substitute it in and the equation will be true. Substitute 0 for I and S minus for S. And there's this constant that we don't know yet. Now, if that same curve passes through S plus 0, then this point also lies on the curve. So we substitute that into this curve. I is 0 and S is S plus. We still don't know C. Actually, we don't really need C. C equals the opposite of this number. C equals the opposite of this number. These two numbers are equal, actually. They're both minus C. So we just set these two numbers equal to each other and then kind of group things so everything looks nice. And we end up with this equation, minus S plus minus S minus plus gamma over beta log S plus minus S minus equals 0. So that's the equation that relates S plus and S minus. If you knew S minus, you would just have an equation for S plus, and there's not really a formula for S plus, but it can be calculated numerically. We made a little graph here. One thing that's particularly important is if you take S plus equal to 1, where everybody in the population is susceptible. So that's the case with a new disease. Nobody in the population is immune to it. It's never been around before. So set S minus equal to 1 and just calculated 1 minus S plus as a function of R naught. It depends only on R naught. It doesn't depend on gamma and beta separately. You get 0 for R naught less than 1. Nothing really happens there. But as soon as R naught gets greater than 1, the total number of infectives starts increasing. Here you might want to look at R naught equal 3. That was a common estimate for COVID-19 at the start of the pandemic. And what you find is that something like 95% of the population ends up having gotten sick before the epidemic ends. Another important number to look at for a new epidemic where nobody in the population is immune yet. Let's go back a few slides. The epidemic starts, the number of infectives grows. Here's the peak number of infectives before it starts to fall. That is also of interest. This will give you an idea of the maximum pressure on your healthcare system, the peak number of infectives at one time during the epidemic. That can also be calculated numerically. We did that. Here it is. The maximum value of I is a function of R naught when S minus equals 1. So you only really get something interesting when S naught is bigger than 1. It gradually increases. I just calculated it for R naught up to 20. Let's take a look at R naught equals 3, a good reasonable estimate for COVID. What you end up with is 0.3. So during an epidemic with R naught equal to 3, the maximum number of people in the population who would be infective at a single time is around 30% of the population. That's a really scary number. Let's discuss how realistic a number like that actually is. It's absolutely correct given the model, but the thing to take into account is that if an epidemic of a bad disease starts, various things are going to happen. People are going to do things, governments are going to do things. And in terms of our model, what that means is that people are going to try to control that number beta. So remember, R naught is beta times 1 over gamma. This is what decides everything about an epidemic. There's not much to do about gamma. Remember, 1 over gamma is the length of time that people on average are sick with the disease. There's not much that can be done about that unless, well, perhaps a good drug is developed that shortens the length of the disease. But beta can be controlled by people, or people can affect it. So what was beta? Remember from the first lecture, beta is the number of people contacted by an infective person in a day times the probability that the disease is transmitted by that contact. So it's the type of contact that would normally transmit this particular disease, but no disease is passed on with probability 1 when a contact takes place. So we have to multiply by a probability of transmission. So what steps can be taken to reduce beta? One is to quarantine infectives. Just make them stay home. Then they're going to contact fewer people in a day. They'll contact the people taking care of them, but that will be fewer people. Another thing we could do is quarantine people who might be infective. You know, with a lot of diseases, when you contract it, it takes a little while before you come down with symptoms and you know you're infected, and before you know you're infective. So you might want to take people who have been in contact with infected people and just quarantine them on the chance that they might become infective. These are steps that the government could take. Another step a government might take is to close businesses, close schools, at least impose a lot of restrictions on them, like say that you can't have very many people in a restaurant, that sort of thing. When a government does that, it is trying to restrict the number of people that an infective person comes into contact with per day. If you close the schools, people don't come into contact with anybody there. If you try to keep people at some distance apart in a restaurant, then they don't contact them close enough to pass on the disease. Okay, so these are all things a government might try to do. But whether the government's doing anything, what we observe during epidemics is that people take steps on their own. If they can, they stay home so that infectives won't come in contact with them. If they have to go out, they might wear a mask. What that does is it cuts down the probability of transmission when they come into contact with an infected person. So all these steps can reduce beta and thus mean that the number that you calculate from the model isn't actually what happens. It's not that the model's wrong, it's that people in governments take it upon themselves to make the model change. You've heard of herd immunity. When S declines to gamma over beta, the number of infectives in the population starts to decrease. Gamma over beta is 1 over R naught. So when S falls to gamma over beta, the rest of the population, I plus R, must add up to 1 minus gamma over beta, or 1 minus 1 over R naught. So that's what's called the herd immunity fraction. When the fraction of the population that either infective and about to become immune or already immune gets up to 1 minus 1 over R naught, the disease will start to fall. For example, if R naught is 3, when the population fraction that's infected or immune gets to 1 minus a third or 2/3, the number of infectives is going to start to fall. You can get to herd immunity just by letting the disease take its course. A quicker way with less illness would be to come up with a vaccine, vaccinate a lot of people, get a lot of people into that immune recovered category without ever making them go through coming down with the disease. Let's briefly discuss the SIR model for a disease that's sometimes fatal. So now we're going to have 4 compartments: the susceptible compartment, the infective compartment, and this time people will go from the infective compartment either into a well compartment when they recover, or if they die, they will be deceased. That's another compartment. Mu is the rate at which infectives get well, mu I. Delta I is the rate at which infectives die. So the differential equations for the population fractions here would be S dot equals minus beta SI, as before. This time I dot is plus beta SI, but now I can decrease in 2 ways: minus mu I to the well, minus delta I to the deceased. The wells increase at the rate mu I, the deceased at the rate delta I. Beta has exactly the same meaning that it did previously. It takes a little thinking to figure it out, because now the fraction of the population that's susceptible, if you look at a model with n people, it's not S over n because some of the population is deceased. It's S over the remaining population that's alive. So you have to be careful about calculating this, but that's done in the text. I'm not going to go through it now. So here's our differential equation. If we just define a compartment R is W plus D in terms of algebra, we're just combining the well and the deceased into a single compartment R, then what would the differential equations be? So I dot now will decrease at a rate, well, let's just write it as mu plus delta times I. And R dot, since we're combining these 2 compartments, R dot will be mu plus delta times I. The thing is, I mentioned this at the beginning of the lecture, this is exactly the SIR model. Just set gamma equal to mu plus delta, and you would get exactly the SIR system of differential equations. In this case, the R compartment is called removed, since it includes both people who become well and people who become deceased, but the differential equations are exactly the same. SIR is a good model to use at the start of an epidemic of a new disease that we don't know much about. SIR is what's called an epidemic model. It does not take into account long-term processes such as eventual loss of immunity, which might take place very slowly, vaccination, eventually a vaccine might become available. It doesn't take into account natural births and deaths in the population. Even if you were to let an epidemic run its course and get the infectives down extremely low, new susceptibles get come into the population by getting born if there's no vaccine for newborns. And this is a long-term process that should be taken into account. So at the start of an epidemic, these very long-term processes, births and deaths, are not relevant. You may not even know how long it takes before somebody becomes immune. Vaccines don't exist yet. So the SIR model is a good model to use at the start of an epidemic. It's called an epidemic model. And this is where we will conclude the lecture. Thanks for listening.